Right, so in this hour we are going to discuss about solving flowsheets and the links between the flowsheets and the process units. So I remind you that the flowsheet is a list of process units that are interconnected by flows of material flows, and also flows of energy being the power or being the heat load in some cases. And we know that the process units are processes that are going to convert flows in the system by realizing thermodynamic conversions that needs to be modeled. Which depends on the type of technology that is used, that depends on the size of the equipment that are available. So this is a flow sheet, and my goal is to show you today how we can solve those flow sheets. So last week we have seen that in order to model a process unit, the first element that we were needing was a thermodynamic model that was able to characterize the states of the different flows that are in the system. And we have identified that in order to be able to characterize the flows, it was important to know the n plus 2, so n being the number of compounds, plus 2 variables. If I want to be able to calculate all the rest of the properties that characterize the state. And when I'm saying n plus 2, is that n plus 2 with one additional condition, is that at least one variable needs to fix the flow. Okay? So knowing that we have at our disposal what we name the constitutive equations that allow us to calculate the thermodynamic properties of any of the flows, then my goal today is to look at the model that is going to transform the flows that are entering the system into the flows that are leaving the system. And this operation is depending on some operating parameters, so characteristics of the process unit. And we are going to write a list of equations. And among all the equations that we have to write, the balance equations are the first one that we will always write, because we know that this is the basics of the description of what is happening. Okay? We know that the mass and the energy balances will have to be satisfied. So it means that I can always write these equations. To those two equations, so or set of equations, so the mass balances and the energy balances, I will have also to add an equation that is going to tell me what is going to happen with the pressure. And this will be the impulsion equation that mainly is going to fix pressure drops. And then I will have a list of equations that I will name the performance equations that are going to describe what is happening, what are the phenomena that are used or implemented in the technology, like heat transfer, like expansion, that will allow us to model the thermodynamic transformation. So mass and energy balance is always there. Impulsion balance, which allows to fix the pressure, needs to be set. And then afterwards, the performance equation that describes the process unit operation that is happening inside the unit. When I'm looking at the balances equations, they have a generic form. And the generic form is shown here. And it's going to tell me that the accumulation is equal to what is entering minus what is leaving, plus what is generated minus what is consumed. So this means that what is entering is going to leave until it is consumed or produced inside or is generated inside. Okay? The accumulation term is representing, for example, what is happening if you have a vessel that is accumulating water, okay, that remains inside the system. And the rest is, in fact, calculated first by looking at what we name the control volume. So we have to define the system and the border of the system. And in our case, in the case of a flow sheet, the border of the system is the connectivity with the outside. So typically, it's where I'm connecting pipes, okay, or cable, right? And then I will look at what is entering via this border, so the control volume, and then what is leaving. And then I have to add those two terms, the generation and the consumption term, which is mainly representing, on the one hand, the possibility that I will generate by a chemical reaction a chemical compound, or I will generate electricity by using heat. Okay, so this is the part where there is the generation and the consumption in the system. In most of the cases that we are going to study, we are going to define a system without accumulation, which is named the steady state. So it's when a system is just operating in a constant way without having any accumulation inside. So I'm not going to produce hot water, I'm going to produce heat. Okay, which means that in this case, what is entering the system is going to leave the system, considering also that there is a generation and a consumption in the volume. Now, if I'm now looking at the list of equations that I will be able to write, for each of the compounds, I can write a mass balance. I can write a mass balance for what we name a network. So it means interconnected tubes inside the system. Okay? I can write the mass balance. Then for the whole system, including the work that is entering, including the heat that is entering or leaving the system, I will write the energy balance. And I will have also to write something which is the impulsion balance, meaning that I will have the number of components plus two equations. Okay? This is assuming that there is no chemical reaction. If there are chemical reactions, then the balance will deal with the atomic balance instead of working with the components balance. Okay? Because atoms will be concerned, but it's possible that there will be chemical reactions inside. Okay? Now, something which is important, I have to look at the form of the equation. So, the mass flow that is entering is going to leave can be written in this way. So, just the convention that it is accounted positive when it is entering the system. So, it means that this one is, in fact, entering in this sum as a negative value. Okay? And I can write this for each of the compounds, okay? And the fact that there is no accumulation means that this term is equal to 0. And this is going to express the material balance. On the other hand, the energy balance will be written by considering all what is entering via the frontier and what is leaving on the frontier. Again, I'm using the convention of the plus here, meaning that it is positive when it is entering the system, okay? And I can write therefore the energy balance by saying, okay, the mass flow multiplied by its energy content, and the energy content of the flow is represented by the enthalpy. The enthalpy that is calculated, we have seen last week, by the constitutive equation that makes the links between the temperature, the pressure, and the composition of the flow. To which we add the contributions of heat and the contributions of work, and we say there is no heat energy accumulation in the system, meaning that the variation is equal to 0. The fact that we have to use the constitutive equations to calculate the enthalpy and to link the temperature, the pressure, and the composition with the enthalpy content to be able to write the energy flow, to calculate the energy flow, means that we will, those equations will be non-linear. Okay? So it's only in one case that it will be linear. That this enthalpy is linear is when you can assume that the Cp is, so the specific heat is a constant with respect to temperature, which is not always the case. But in addition, you can see that even if this equation is linear, this is going to introduce a bilinear term. It means that the equation will be nonlinear. Okay? Okay, now I have the list of equations, and I know those equations are nonlinear. I have also something which is important, is to identify what I want to calculate. If I want to do a calculation, it means that I will have to make the list of all the equations that I have and all the variables that I would like to know. Okay, so it means that I would like to know the state at the inlet, the state at the outlet. I would like also to know the value of the parameters here. Okay, meaning that I will be able to calculate, as I was doing it before, the degree of freedom of the system by making the difference between what I would like to know, which is the number of variables, the value of all those variables, and the information that I have already, so the number of equations. Okay? So what I can see here is that I have the mass balance, the energy balance, impulsion balances, plus modeling equations. Plus things that I know that I will be specified. So for example, most of the time I will consider that what is entering the system is known, so I know the temperature at the inlet, I know the pressure at the inlet, or the composition at the inlet, which I will name the specification equations. Okay? And when I'm making the difference between the sum of all the equations here, which is NE, and the deducing this amount from the NV, which is what I would like to know, I will have what we name the number of degrees of freedom of the system, which is the number of values that I have to add in addition to be able to have enough equations to calculate all the values of the variables. Okay, so this is the number of degree of freedom. And what is interesting is that it has to be accounted by considering that I have the constitutive equation. So it means that I'm looking here only at the NC plus 2 variables, not the other ones that I need. So enthalpy, entropy, etc. I know that those values will be added in the list of equations. By the activation of the constitutive equations. Okay, so first thing, identify the degree of freedom of the system, which allows me to know how much values I have to specify. In order to understand a little bit more what is inside the system, and if I can solve a set of equations, there is a trick that is typically used, which is the incidence matrix. And the incidence matrix is going to look at making the link between the equations and the variables. And I'm first going to say, or to record, if one variable is a member of one equation. And this is what is the incidence matrix representing. So for example here, I will have the mass balance, which implies the inlet flows, for example, and the outlet flows. Okay? And I will make the list of who is influencing what. So for example, here I have the parameters of the units. So the parameters of the units will only appear in the modeling equation of the unit. But they can also appear, like for example, here, in the, here, in the specification. So if I have to add, if I'm going to say that the area is fixed, then I will have a cross here, which defines the specification of the area. Okay? And I will be able to solve the problem if the incidence matrix that combines the list of equations and the list of the specification is a square matrix. So it means that I have enough specifications to fix the degrees of freedom. And if all the equations are independent. Okay? So it means that there is another conditions rather than just having the number of degrees of freedom. So if I'm looking at what I have there, in fact I have the modeling equations and the specification equations that fix the degrees of freedom. So now let's look at what it means when I have a simple model, like a turbine. Okay? If I have to model a turbine, I'm going to first declare what I would like to know, which are all the variables that I will deal with. So the output and input conditions, the isentropic efficiency of the turbine, and the mechanical power that the turbine will deliver. So I make the list of all the values that I would like to know here. And then I'm going to make the list of all the equations. So I can write the mass balance here. So the flows that are entering is equal to the flow that is leaving. The energy balance that says that the mechanical power produced is the difference of the enthalpy content of the enthalpy flow at the inlet minus the enthalpy flow at the outlet. Composition equations that says that the composition is the sum of the concentration is equal to 1. And then the modeling equations that are, for example, telling me that the mechanical power is equal to the isentropic power multiplied by the isentropic efficiency, and that the isentropic power is calculated by making the difference between the enthalpy at the inlet and the enthalpy that results from the expansion, the isentropic expansion. And the isentropic expansion is calculated by saying that the entropy at the outlet, with the pressure at the outlet, is equal to the entropy of the inlet. Okay? And if I'm making this list of equations, making the list of all the variables that I have, and the list of all the equations that I have, I realize that if I'm assuming that the inlet conditions are specified, I need to fix two values in order to be able to calculate the my turbine. And the two values are quite straightforward here. I have to fix the pressure at the outlet, and I have to fix the isentropic efficiency. Okay, if everything in the inlet is known. Okay. By the way, if I'm considering that I fix the temperature here, then the isentropic efficiency will be calculated or can be calculated. Okay, so it means that now I have defined the list of variables, the list of equations, and I can translate it into an incidence matrix. You can note that I have first added the specification equations on the top, and then afterwards the balance equations, the modeling equations, and as well the constitutive equations. Okay? So now the question is, how do I solve this set of equations, which is a set of nonlinear equations? And I have two strategies. The first one is the one that you have applied by applying optimization techniques with Ample. Just solve a set of equations. So find a value of x in such a way that all the equations are satisfied. Okay? Newton-Raphson methods need an initial point and do iterations. Okay? And the problem is nonlinear, so it means that you know that you will have to do iterations. So from the practical point of view, what does it mean? It means that you will have a model that will be represented by a list of equations. So pay attention, for example, that here, I'm not saying that the mass at the outlet is equal to the mass at the inlet. Okay? What I'm saying is that the difference between the variable that represents the mass at the outlet minus the value of the mass at the inlet is equal to 0. Okay? And so I have to find the value of mass in and mass out in such a way that this equation is equal to 0. And I will do it for the calculation of the enthalpy, I will do it for the isentropic enthalpy, I will do it for calculating the enthalpy at the outlet, and I will do it for the calculating the temperature, and I will do it for calculating the energy balance. And at the same time, I'm going to fix the values of some of those variables by saying that the value of the mass at the inlet is equal to the specified value that I have imposed. And I'm writing this as an equation. I'm saying this value minus this value is equal to 0. Okay? And I know that I can solve this problem using the Newton-Raphson method. Okay? There is, however, another way of solving the problem. And the other way of solving the problem is what we name the sequential approach. The sequential approach is going to look at the incidence matrix and try to put one variable on the diagonal. Okay, so what I'm going to do is that I'm going to make a rearrangement, change the order of the equations and the variables in such a way that I will have for each of the element of the matrix one element in the diagonal. Okay, so if you remember when you have been looking at numerical analysis, solving a linear problem in inverting a matrix, the trick was the LU decomposition, and the goal was to find one element on the diagonals. Okay, so we do exactly the same here, permuting the rows and the columns in such a way that you have one element, non-zero element, in the diagonal. Okay? So it means that if I have this, then what I can do is that I can say that, okay, the first equation is going to calculate this value. The second one is going to calculate this value. The third one is going to calculate this value. And I'm going to do it like this. And as soon as the values that are in the incidence matrix are such that they are in the lower part of the matrix, then I know that I know this value, so it means that I will be able to calculate the mass out, for example, knowing the mass in. Okay? And if I'm doing it like this, I will continue up to the end, and I will have a sequence of resolution. Each time I'm solving one equation, I'm calculating the value that is here on the diagonal position. Okay? So what it means is that I have associated one equation to the calculation of one value, and this equation will always use the values that have been calculated before. Okay? So it means that now I can transform the equations by having an explicit form in which I will have a given value that is equal to a mathematical formula that depends only on values that have been already calculated. Okay, so for example here, I will, knowing that the flow in the inlet is specified, so it's known, then I can calculate the value of M out. Knowing the composition, I can calculate the composition at the outlet. Knowing the temperature, the pressure, and the composition, I will be able to calculate the enthalpy. Knowing the temperature, pressure, and composition, I will be able to calculate the entropy at the inlet. Knowing the entropy that I have calculated, and knowing the pressure that is calculated, and knowing that this is known now, I will be able to calculate the isentropic enthalpy of after the expansion. Knowing this value and knowing the isentropic efficiency, you can see that I know everything here. I will be able to calculate the enthalpy at the outlet. Knowing the enthalpy at the outlet, I will be able, by using the constitutive equation and knowing the pressure and the composition, I will be able to calculate the temperature. And knowing the enthalpy at the outlet and the enthalpy at the inlet and the mass flow, I will be able to calculate the work that is produced. Okay? So now I have made a sequence of resolution to solve the problem, and I have transformed each one of the equation in an explicit form. Value equal something which does not depend on the value. Okay? And this is something that you do, I would say, quite intuitively. That's the way you have learned to do it. Huh? Okay? So here I'm just showing you that it's a really systematic way of solving the problem. Okay, so we have a very nice sequence in this case, but it's not always possible to do this. Okay? It might happen that sometimes you will have a situation like this where you have exactly one element on the diagonal, but you still have compounds on the U side, so the upper side of the matrix. So in this case, what you can do is to say, okay, why don't we use what we know from the solving procedure? We know that the equations are nonlinear, but what I can do is that I can solve, if I'm fixing a value for this variable here, then I can calculate the diagonal by solving this equation here. Okay? And at a certain time, I'm going to recalculate the value, because the value that was here is on the diagonal here. So it means that I'm going to calculate the value of this parameter here, of this variable here, by solving equation 8. Then I will be able to solve equation 9, and I will go to equation 10, and the equation 10 is going to give me back the value here. Okay? And then I'm going to do an iterative procedure. I'm guessing the value of the element that is on the upper side here. I'm calculating, therefore, those elements here, and I'm going back and recalculating the value, and I have to test if I have converged. So it means that it's an iterative procedure with an epsilon that needs to be selected, which will work on the difference between the new value here, so the new value that has just been calculated, and the previous one. And then I will have to go back to redo the sequence until I'm satisfied. So it means that until the value that I'm calculating is close enough to the value that I have guessed. Okay? And by doing this, then I will be able to still solve the sequence. Okay? And this would be, for example, the case on the turbine. If instead of having a constant isentropic efficiency, I have a formula of the isentropic efficiency that is a function of the expansion ratio and the mean volume. Okay? And this is typically what you receive from the literature. So in this case, I need to know the mean volume here. I need to know the temperature at the outlet, and I need to know the temperature of the outlet. I will calculate, the temperature at the outlet by knowing the value of the isentropic efficiency here. So it means that I have to make an assumption. So what I will do is that I will assume the value of T out here. I will make the calculation of the isentropic efficiency, which will give me the new value of the T out here. And I will test if this value of T out is similar or close enough to the new value from the previous one. And if yes, then I can continue by my calculations. Otherwise, I have to loop and restart the calculations with a new value of T out. Okay? So this is the method for solving in a sequential way a process unit. Okay. You can do it for a compressor, you can do it for a heat exchanger, you can do it for a distillation column, you can do it for a fuel cell. Okay. Just that you have to be smart enough to define the sequence, to identify the diagonal elements, and to define the sequence of resolution. So now the two methods can be applied. So we can always decide that we are going to make a sequential approach or a simultaneous approach. And there are differences. So for example, if I have to change the functionality of my model. So for example, my turbine was calculating the work that is produced by the turbine. Okay? In the case of and now let's assume that instead of calculating the work, I would like to know what is the flow for a given work. Okay? And the flow can depend on the isentropic efficiency, etc. Okay? So if I want to do this, in the case of a simultaneous approach, it's quite simple. I just have to change, instead of having mass flow minus specified value is equals 0, I will have work minus specified value equals 0. I do not change the equations here, they remain the same. I do not change all the specifications, only one is going to be changed, and apply Newton-Raphson and you have the solution. So very easy from the programming point of view to to make this development. Okay, it's a little bit different if I have to do the same with the sequential approach, because the specification of the flow was my first equation, and now I had to change the sequence, because what I will have to do is that I will have to start with the composition, calculate the enthalpies and the entropies, then calculate and at the end obtain the specific power that I can then divide by the specified work that is needed to obtain the flow. Okay, and so what it means is, it means that if I have to do this and I have to make a programming in MATLAB, then I have to rewrite the set of equations, hoping that I will not make an error by cutting and pasting equations. Okay? And typically what is going to happen is that you will have, even if you use MATLAB or Python, you will have a function that is going to make represent the turbine, and you will specify the mode, which is going to say use this sequence or use this sequence, right? Which makes it, let's say it's a little bit more risky, because you will have a lot of code, and if you make an error in one of the sequences, then you have to correct on all the sequences, which is not always so easy to realize. Another way is to say, okay, I'm still going to use the same model here, and the only thing that I will do is that I will look at the end if the work that I have calculated is the right one, and if not, I'm going to modify the flow. So what I'm going to do here now is calculate a new value for the flow and make an assumptions about the specification of the flow at the inlet, and then I will converge until up to the time where there is, I'm satisfied with the specification which will be tested here. Okay? In this case, the system will be linear. So if I'm applying the simple methods that I know to solve nonlinear equations, I will calculate the derivative. And after one step, I will have obtained the flow in the system. Okay, so now what it means, on the one hand, simultaneous approach just change the set of equations of specifications. In the case of the sequential approach, either change the sequence or add a loop on top of the sequence. Okay? And don't forget that as soon as you do a loop, you will have to test the convergence, not only on the specifications, but also on the variations of the variables that you can manipulate. But this will allow you to use the model for different purposes. So it means, and I give you the example here, now what I can do is I can calculate the heat exchange area that is needed. Okay? But I can also calculate the heat load if the area is fixed. Okay? Just by changing the specifications, and in the case of the sequential approach, by changing the sequence. But I can also do parameter identification. So if I know the heat load and the area, then I can calculate the value of the parameter, which is the heat transfer coefficient. Okay? So it means that I will be able to use the model for different purposes. And this will be important because sometimes I'm going to use the heat exchanger model to calculate something related to measurements. And then afterwards, when I will have the heat transfer coefficient, for example, that is identified, use the same model to calculate what is happening if I'm changing the operating conditions on this heat exchanger that I have observed in the past. Okay? And I will use, obviously, the same model if I want to be consistent between the calculations I'm doing. Okay? So it means that we have to be just consistent in the use that we are going to make of the model. So something which is important is that we have always to use the same level of detail and the same set of equations to represent the same equipment. Otherwise, So we measure our inefficiency rather than measuring the inefficiency of the unit. Okay, because then you are, if you are using different sets of models for representing the same thing, then it just means that you are not mastering really the use of the model. Okay, so conclusion. Units can be solved in two different ways: simultaneous or sequential. Okay. At the level of the problem statement, a simultaneous approach will have the incidence matrix that will be automatically generated because it is written in the equations. In a sequential approach, you will have to do a degree of freedom analysis. Okay, this is important, and you will manipulate the equations to identify the sequence, so the list of equations. From the robustness of the model's development, then a simultaneous approach is much more robust because you write once only the equations and then you just play with the specifications. While if you have a sequential approach, then it means that you will have modes or whatever. But there will be something which will be important, and when you are developing models, is that in some cases the set of equations can change due to some conditions. So, for example, there is a phase change or not a phase change. Okay. With a sequential approach, it's really easy to say, well, if these conditions, then use this equation. If this condition, use this equation. In a simultaneous approach, this is much more difficult to do. Okay. You have seen the example with the generation of one of the equations in the heat transfer. You have to switch the equation, or you have to find another formulation of the same equation, just to be sure that the system is able to solve. So the if then else part will be much easier in the sequential approach. And the last dimension is when you have to solve an optimization problem using this model, you know that you will need derivatives. Okay? And if you are using a sequential approach in which there are iterations, then you will have to be really smart because the model will include all the values that you will get for calculating derivatives by perturbations, will depend on the values that you have selected for deciding if you have converged or not. So if you have iterative processes, they will create noise. Okay, and it will be important for you to be aware of this. Right, so now I have a way to solve units. The next step is to assemble units and make flow sheets. That means that for each of these blocks here, I have a possibility of calculating what is the outlet, knowing the inlets. Okay, I have this one, etc. So I have all this information. But now I would like to calculate what is the amount of electricity produced. In this case, it's a fuel cell. What is the amount of electricity produced as a function of the flow of methane that is entering the system, and as a function of the temperatures that are specified. So what I'm going to do is that first I'm going to look at, and this is a very simplified flow sheet. Okay, I'm going to have to make the degree of freedom analysis, but not for the process units, but for the whole system. Okay? And what will be the difference is that now the values that are characterized in the outlet of this first unit will be used in the next one. So those are the same variables. So that's like if I have added an equation of connection, which will decrease the number of degrees of freedom, because now the flow that is entering this unit does not have to be fixed anymore. It is the result of the calculation of this one. Okay? So what does it mean? It means that I will have to do the number of degrees of freedom analysis by making the sum of all the equations that are in all the modules that I have in my flow sheet, by making the sum of all the variables that I would like to know, meaning that I will have the inventory of all the flows that I have in my system here, and for each of them, make the list of compounds that are concerned to identify the number of variables that I would like to know. Okay? And making the list of all the equations that I have, making the list of all the variables that I would like to know, I will calculate the number of degrees of freedom for the whole system now. Okay? I'm looking now at the whole system and the unit interconnections. And now the question is, how do I solve the flow sheet? So solving the flow sheet means that I would like to know the value of x0, x1, x4, x3, and I would like that those values are calculated in such a way that the equations of unit 1 are satisfied and the equations of unit 2 are satisfied, and that I have reached the specifications that I have added in such a way that my number of degrees of freedom is equal to 0. Okay? And again, there are two ways of solving the problem. The first one is to use a simultaneous approach. And the simultaneous approach will be just making the list of all the equations, here, making the sum. I can even consider that the variables at the inlet are different from the variables of the outlet, and I can add an equation that says that the value of x1 is equal to the value of x2. Okay, which is a new equation that I'm adding to the system. Typically, we are going to make a substitution directly, saying that the variable x1 is the variable x2, so that we do not have to solve this equation. But we could add the same in the same way. And now I will have the list of equations. I will have the list of variables, and the equations are nonlinear, meaning that I will use Newton-Raphson in order to solve the set of nonlinear equations and obtain all the values that I need in the flow sheet. This flow sheet can also be solved in a sequential approach. In a sequential approach, I will have to, however, consider that at a certain time, so for example, I can solve this unit and calculate the outlet, then I will transfer the data to the next unit and then solve the next unit. But then what you can realize here is that the outlet of this unit is used as an inlet to this one. Okay? So it means that it's like if I have an element at the upper side of the LU decomposition. Okay? And what I'm going to do then is that I'm going to say, okay, I can solve the problem if I know x5. So let's assume a value for x5. Then let's solve this equation, this unit here. It can be solved by a sequential approach. Let's calculate x1. Then let's transfer the value of x1 into x2. Then solve the second unit, unit 2 here, to calculate x3 and x4. Now what I'm going to do is that I'm going to consider that the value of x4 should be the same of x5, and I'm going to test if it is true. Okay? And it's very important to test it, okay? Because this is a sequence, so it means that if I'm not testing it, I would perhaps just take the value and put it there, and this would not be the good idea, because then you will not know if the initial guess was the right one. Okay? So what you will do, therefore, is to do what we name a tiering. It means that by tiering, we explicitly say, I need to guess this value in order to make the calculation of U1 and U2, but I need to verify that my guess was correct. So it means that when I will calculate x4, I will compare it with the value of x5, and I will stop doing this sequence if the x5 is close enough to x4. Okay? Very important. So I'm tiering, and tiering means assuming a value and testing that the calculated value is the one that was expected. Okay? But if I'm doing this, then I will be able to solve a flow sheet by a successive solving of units one after the other. And in order to calculate the new value of x5, it does not have to be x4. It can be the calculated value of x4, but it does not have to. Then I have all the methods that I know to solve nonlinear equations. Okay, simple substitution or Newton-Raphson if you wish, okay? Or chord or whatever. Okay, so you have the list of methods that allows to do the convergence. In conclusion, when we have to solve flow sheets, we can use sequential or simultaneous approaches. Okay, and knowing that we are quite good in understanding the numerical analysis, we will realize that on the one hand, if we have to define the sequence of resolution, we have to organize our calculations step by step, one after the other. Okay? And it means that we will have to define the sequence, and this is something that I'm going to discuss next week. And on the other hand, we know that we use a simultaneous approach, as we are going to use an iterative method because we know the equations are nonlinear. It means that we need to know an initial guess, okay? And something that I can tell you is that the best way of finding a very good initial guess for simultaneous resolution is to define a sequence of initialization. Okay, so it means that the two approaches will in fact be used together. Sometimes it's easier to define an initialization sequence than a flow sheeting sequence, but you will need, at least in your mind, to define a sequence which allows you to define what will be the most or the better initialization for the set of equations. Once the set of equations or variables is initialized, meaning that you know the value of all the variables which are not far from satisfying all the equations, then you can apply the simultaneous approach and the Newton-Raphson. Okay? Do you have questions about this? You will have the occasion of applying these tools. So this afternoon, Alessio will present you the methods for that is not the method, the tools that you will use, which are professional tools that will activate all what is needed to do calculate a flow sheet. So calculating the constitutive equations, calculating and solving the mass and the energy balance in a systematic way. Okay?